List and describe a method used to measure motor speed. Motor speed is the measure of how fast the motor shaft is rotating. For example, the motor shaft shown here is turning at the rate of 1 revolution per second. The rotational speed of a motor is usually given in units of revolutions per minute, or RPM. Therefore, the speed of this motor is 60 revolutions per minute, or 60 RPM. Instruments that are designed to measure motor speed are called tachometers. There are several types of tachometers, each based on a different method of measurement. Two common types of tachometers are handheld tachometer and phototachometer. The handheld mechanical tachometer works much the same as a car speedometer. It has an internal gear system that converts the rotating motion of a shaft into a reading on a dial. To take a reading with the handheld tachometer, its rubber-tipped shaft is held against the spinning motor shaft, causing the tachometer shaft to spin at the same speed as the motor shaft. The dial then indicates the rotational speed. The phototachometer uses a beam of light pointed at a piece of reflective tape that has been placed on the motor's shaft. The phototachometer counts the number of times the tape passes through the light. Once the speed has been determined, it is shown on the display. This method has an advantage over the handheld mechanical tachometer because there is no need for direct contact with the motor shaft. However, some models have attachments which enable direct readings if necessary. List 2 applications for measuring motor speed. Two applications where motor speed must be measured include: check for a motor overload condition, performance of electrical speed controls. When the motor is overloaded, the speed decreases drastically from its rated speed. Electrical speed controls relate mainly to DC motors where speed is easily controlled by electrical control of input voltage and current. Measure the speed of a motor using a phototachometer. In this procedure, you will connect the DC motor in the shunt configuration. You will then operate the motor and use a tachometer to measure the rotation speed of the shaft as you vary the speed. Click on the equipment to view the step-by-step instructions for performing this procedure using the selected system. Define torque. Torque is a measure of the turning effort caused by a force acting on a part that rotates. As shown in the graphic, the amount of torque created by a person to turn a bolt with a wrench is caused by applying a force at some distance from the pivot point of the rotating part. In this case, the rotating part is the combination of the wrench and the bolt. The amount of torque created is determined by the amount of force applied and the distance from the pivot point to where the force is applied. This relationship is expressed in the formula shown. The units of torque measurement are a combination of the force and distance measurements. For example, Newton meters is the SI metric unit of torque measurement, where newtons is the force measurement and meters is the distance measurement. The same is true for the U.S. customary torque units, where pounds or ounces are the force measurements and feet or inches are the distance measurements. Torque is increased by either applying the force farther from the pivot point or by increasing the amount of force applied. Calculate the torque applied to a bolt given the information shown. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Calculate the torque applied to a bolt given the information shown. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Calculate torque given force and distance. In this procedure, you will calculate the torque using the torque formula. Click on the pencil and paper to view the step-by-step instructions for performing this procedure. Describe how motor torque is developed. Torque is developed in an electric motor because of the interaction of different magnetic fields. These magnetic fields are created by windings in the stator and the armature. Shown here are the stator windings. Also shown is a looped conductor that has been placed inside the stator windings. This looped conductor represents a rotor or an armature winding. When current flows through the looped conductor, which is part of the rotor or armature, a magnetic field is created around the conductor. This is where the laws of polarity come into play. Like magnetic poles repel, and unlike magnetic poles attract. This action causes the looped conductor to rotate around a pivot point. The magnetic field around side A of the looped conductor has the same polarity as the stator magnetic field. Therefore, that side of the conductor is repelled from the stator field. The magnetic field around the other side of the looped conductor has a polarity opposite that of the stator field. This causes side B of the conductor to be pulled toward the stator field. This repelling and attracting action causes the looped conductor to begin to rotate around a pivot point, which in the case of a motor is the shaft. The current flow in the rotor of a motor may be caused either by a power source directly connected to it, or it is induced because the magnetic field created by the stator windings, much the same way as the primary coil of a transformer, induces current flow in the secondary coil. The rotor of a motor is made up of many looped coils, or in some cases, magnetic strips attached around the shaft. This allows an almost continual attracting and repelling action to occur, as long as current is flowing. This helps to maintain the rotation. The concept of creating rotation by interacting magnetic fields is true for all electric motors. However, the method for creating these magnetic fields varies from one category of motor to another. Define motor load and explain its effect on motor operation. To turn a load, the electric motor must generate a torque that exceeds the torque requirements of the load. The load on an electric motor is the amount of torque the motor must generate at its shaft to overcome the resistance caused by the device the motor is driving. If the resistance that is caused by the driven device increases, the load on the motor also increases. The effect a load has on a motor is to cause the motor to draw more current to produce the torque needed to keep the motor rotating. The speed of a motor also decreases as load increases. The amount of decrease depends on the type of motor. The speed of some motors only decreases a little, and the speed of others decreases greatly. The way in which the motor is coupled to the device it is driving can also have an effect on the torque that the motor needs to generate. In some cases, the motor may be directly coupled to the device it is driving, as shown here. However, in many applications, this is not the case. Electric motors often drive other devices through some type of gear or belt drive. By using these types of systems, a motor is often able to drive a load much larger than it would normally be able to drive. Describe how to calculate the load on an electric motor with a gear or belt drive. The torque that a motor must generate when driving a load through a gear system depends on the relative sizes of the gears. As an example, the motor shown here is driving a load through 2 gears. The torque needed to turn the load is 20 Newton meters, but the torque that the motor must generate is only 10 Newton meters because of the gear drive. The relationship between the torque input and output of a gear drive depends on the ratio of the number of gear teeth of the 2 gears, as shown in the formula. Using this formula, you can calculate torque that is delivered to the load through the gear system. The same relationship is true for a belt drive system. In this case, instead of a gear ratio, the ratio that is used is the ratio of the diameters of the pulleys as shown in the formula. Determine the gear ratio of the gear system given the number of gear teeth. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Calculate the motor torque needed to drive a load that is coupled with a gear system. The motor is directly connected to the driver gear. The load is connected to the driven gear. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Determine the pulley ratio of the drive belt system given the relative sizes of the pulleys. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Calculate the torque a motor must produce to drive a load that is coupled with a pulley system. The motor is directly connected to the driver pulley. The load is connected to the driven pulley. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Calculate the load on a motor. In this procedure, describe the effect a belt or gear drive has on speed. Not only does the gear or pulley ratio affect the torque that a motor can deliver to a load, the ratio also affects the speed at which a load is turned. If the gear that is attached to the load has more teeth than the gear on the motor, or if the pulley on the load is larger in diameter than the pulley on the motor, more torque is delivered to the load than is produced by the motor. The exact opposite is true of speed. If the gear on the load has more teeth than the gear on the motor, the speed of the load will be less than that of the motor. The same is true of a belt drive system if the driven pulley is larger in diameter than the driver pulley. The relationship of speed change to gear or pulley ratio is shown here. The speed formulas and the ones for torque show that a drive system causes speed to decrease when torque is increased and vice versa. A gear or pulley drive is often used with electric motors to not only increase torque, but also to decrease speed. Most AC electric motors are designed to turn at speeds of more than 1,000 RPM, but many applications need much slower speeds. Since torque is increased when speed is decreased, a small motor can be used in the application. Determine the gear ratio of the gear system given the number of teeth on the driver and driven gears. Round your answers to the nearest hundredth. For example, round 1.025 to 1.03 and round 1.024 to 1.02. Calculate the speed of the load based on the information given here and in the graphic. Round your final answer to the nearest whole number. Calculate the speed of the load based on the information given. Round your final answer to the nearest whole number. Calculate the speed of the load based on the information given. Round your final answer to the nearest whole number. Calculate the speed of a load that is driven with a belt drive or gear system. In this procedure, you will calculate the speed of a load given the speed of the motor and the gear. While there are no direct methods to measure the torque delivered by a motor, there are several indirect methods that can be used to determine torque. Prony brake, current measurements, and dynamometer. The prony brake is one device that is used to load a motor. This device also has the ability to indicate how much load is applied to the motor. The prony brake drum is coupled to the motor shaft, and rests inside a canvas friction belt. As the canvas belt is tightened against the brake drum using the wing nut, the load on the motor is increased. This applies a force to the pivot arm. The force is measured by a spring scale that is placed at a specific distance from the center of the motor shaft. This is the radius distance. The force reading from the scale and the radius distance are used to calculate the torque. Torque is also related to the electrical current supplied to the motor. As motor torque increases, so does electrical current. Most motor manufacturers have already tested this relationship and include with the specifications of the motor a graph that shows the torque versus current characteristics. By using this graph and measuring input current, it is possible to determine the torque. For example, from the torque versus current graph shown, you can see that if the measured current is 2 amps, the torque that can be delivered by the motor is approximately 150 inch-ounces. Current measurement is often used to measure torque in the field because the motor is already connected to a load. Disconnecting the load to connect a dynamometer or prony brake would defeat the purpose of the measurement. A dynamometer is another device that is used to load a motor to determine torque. A dynamometer is basically a DC generator. The operation of a generator is exactly opposite to that of an electric motor. It converts mechanical rotary motion into electrical power. To measure torque using a dynamometer, the shaft of the dynamometer is coupled to the motor, and the housing of the dynamometer is free to rotate, but is held by a spring scale. As the dynamometer To measure torque using a dynamometer, the shaft of the dynamometer is coupled to the motor, and the housing of the dynamometer is free to rotate, but is held by a spring scale. As the dynamometer shaft rotates, it generates electrical current and voltage in its windings that cause a counter torque to be developed. When the housing tries to turn in response to the counter torque, it is held back by the spring scale. The scale displays the torque that is applied to the housing. Give an application for measuring torque. A common application where a technician would need to measure motor torque is to determine if the motor is overloaded. This can be quickly checked by measuring the current. If the current is above the rated full load current, this indicates that the motor is overloaded. Operating a motor in an overload condition will result in a shortened service life for the motor. Measure the torque delivered by a motor using a Prony brake. Clamp meters vary by model and manufacturer, but they all have the same basic components. The basic components are each identified in the image shown. For any meter, the instruction manual provides additional features and their usage, along with safe operating procedures. Other meters may perform additional functions. For our usage, we will use the clamp meter for current readings. Clamp. The clamp is opened and placed around the wire in which you want to measure. Doing this enables you to measure current without disconnecting the circuit and connecting the meter in series. Clamp. The clamp is opened and placed around the wire in which you want to measure. Doing this enables you to measure current without disconnecting the circuit and connecting the meter in series. This is particularly important for AC power applications where current level is often high and dangerous. Mode Select Switch. The Mode Select switch determines meter operation range. Other models may have more or fewer selections or have an automatic range selection. Clamp Trigger. The clamp trigger is pressed to open the clamp jaw to enclose the current carrying wire. Only one current carrying wire should be enclosed in the jaw for correct current readings. Measurement Readout. The measurement readout and LCD display displays all of the measurement data. Hold button. In this procedure, you will use the Prony brake to apply a load to the motor, and then use the torque formula to calculate the torque at different force settings. Determine the torque delivered by a motor using current measurements.